Hello everyone, thank you very much for signing in and watching my live feed, stream rather. I'm Mr. Matt and this is Dr. Tot. Dr. Tot, would you like a cookie? You always want a cookie. I don't think you're going to turn down a cookie. Welcome to Algebra I. Today we're going to continue our discussion about piecewise and absolute value functions. I'm going to increase the pace a little bit through the piecewise functions because we haven't yet gotten to the absolute value subtopic, which we're going to delve into today, but I'll probably end up also making another series just on the absolute value function because it is pretty important. But remember that piecewise functions are just a fancy name for a combination of any other function. The combinations, or the points at which we segment the functions, are dependent on the domain of the individual functions. Domain is a fancy word for acceptable values of x. So the piecewise function in whole is going to be multiple statements and have different definitions, functional definitions within each statement. Those statements are bounded by the domain that they say x can be whatever acceptable value. So maybe x is less than positive 2. So that means for any value including 2 and greater than 2, that function doesn't exist. So that function is going to stop right at x equals 2. Then there might be another function in which is defined over the interval of 2 inclusive to, let's say, positive 4 inclusive. So that function will occur between x values including 2 and up to including 4. And then there might be another function that governs all the rest of the values to the right of 4 or greater than 4. So we're going to look at a few examples of that and then get into the definition of the absolute value. The absolute value is the distance that a value is from 0 on a number line. So practically, a lot of students just remember it that it turns all the values positive. And from a practical standpoint, when you're evaluating expressions or values, that is true. Practically, it does turn everything positive. But the reason it turns everything positive is because it represents the real distance from 0 on a number line. Notice that -6 is 6 units to the left of 0. +6 is 6 units to the right of 0. So because the equal distance from 0 on a number line, the absolute value of -6 and the absolute value of +6 are both +6. So practically it does just turn everything positive, but I wanted you to understand why. It represents the real distance from 0 a value is on a number line. So let me go ahead and share my screen with you, and we'll get into some problems. And just a reminder, because this is a live stream, there is a little bit of a delay between the iPad and the broadcast, but I'll make sure to keep a close eye on that. And let me know if you need me to scroll up or down at any point during the stream. So again, the overarching theme here, piecewise and step functions. Step functions are when they're horizontally, we'll look at that, they look like little staircases, or the function overall looks like a staircase, but they're horizontal segments that are restricted over different domains. Piecewise and step functions are combinations of segments of 2 or more functions. The determining factor of which function occurs at a particular point is the domain of the overall piecewise function. The domain tells you what function you should use within a certain interval of x values. So again, just a few definitions. Domain is just a fancy word for the acceptable values of x. An inclusive domain means that it includes the endpoints or that particular endpoint, and that's often given as either brackets or the less than or equal to sign or the greater than, or equal to sign. So the or equals to means that you can include that endpoint in your consideration. However, if you have an exclusive domain, that means that it does not include the endpoint. And that's usually given if it's if it's using a bracket form of notation, then you would use a parentheses here, or less than or greater than. Notice not the less than or equals to, or not, and not the greater than or equal to. Okay, if you have any questions, then please let me know. Otherwise, I'd like to look at a few examples. So I'm going to give you 3 minutes. I'd like you to graph the following piecewise function. And I'll keep track of time in the upper right-hand corner. At about a minute and a half in, I'll start to graph it as well. Okay, so if we look at this piecewise function, f of x is equal to x plus 2 if x is less than 0, 2x if 0 is less than or equal to x, which is less than or equal to 2, and f of x is equal to 4 if x is greater than 2. So first I drew an x and a y plot and marked off some points. And then I also drew in boundaries depending on where the domain is restricted. So the first function exists only when x is less than 0. So 0 is a bound. So I highlighted that value, x is equal to 0. Then also 2 is another bound because the second function occurs between 0 and 2 inclusive. So I marked off 2, and then the third function occurs in all values, x values greater than 2. So less than 0, exclusive because x is less than 0, so we're going to have a hollow dot at when x is equal to 0. When x is equal to 0, the first function, when we plug in 0 for x in x plus 2, we get 0 plus 2. So when x is equal to 0, y, or f of x, is equal to 2. So we have a hollow dot occurring at 0, 2. And then we notice that we have a slope of 1 implicitly here because it's x plus 2. So if we're going to the right, we would go right 1, up 1, right 1, up 1. That would be the slope of 1 over 1. When the slope is 1, we could represent that as a fraction as 1 over 1, rise over run. So we have a change right 1 for every up 1. If we're going left, however, we need to reverse that logic. So it would be left 1, down 1, left 1, down 1. So I plotted out just two little guiding points of left 1, down 1 in order to trace out what this function, sketch out, I should say, what this function looks like. And then we have an arrow going downward. In between 0 and 2, the function 2x is inclusive to the endpoints, so we have solid dots. And then we have a slope of 2. So we're starting, when x is equal to 0, plugging in 0 for 2x, we get 0. So that's why we're at the origin. We start at 0, 0. And then we're going up 2 for every 1 right. That's what the slope of 2 represents. Rise over run. Change in y divided by change in x. So 2 can be written as a fraction as 2 over 1. So the change in y is 2 for every 1 change in x. So we're going to go up 2, right 1, up 2, right 1 to mark off a few points. Then you can connect the dots. Notice that we're ending at x is equal to 2. Then f of x, when f of x is equal to 2x, f of x would be equal to 2 times 2, or 4. So at x equals 2, f of x is equal to 4, so we have a solid dot at 2, 4. And then for the third function, f of x is just equal to 4, so we have a horizontal line starting at x is equal to 2 and continuing rightward towards positive infinity. The domain, however, is exclusive to x is equal to 2. It's x is greater than 2, not greater than or equal to, so we have a hollow dot at x is equal to 2. If you have any questions, then please let me know. Otherwise, I'm going to give you 3 minutes. Please look at g of x, graph the function g of x. And I'm just looking for rough sketches here. It doesn't have to be anything exact. Okay, so g of x is equal to 3x plus 1 from negative infinity to positive 1 inclusive. So first off, I marked off my domain restrictions. I have breaks at positive 1 and positive 2. So I highlighted those vertical lines, or marked those values with vertical lines on the graph. So before or less than positive 1, the function is governed by the function 3x plus 1. So what you can do, we know that we need to go up to positive 1, so just maybe test a few values below or in the direction of the domain that you are looking for that satisfies the function. So I'm going to test the values negative 1, 0, and positive 1 for this function because this function occurs at those values. That'll give me a few dots to be able to connect and ultimately draw the overall, or sketch the overall function. So when x is equal to negative 1, we get 3 times negative 1 plus 1. 3 times negative 1 is negative 3. Negative 3 plus 1 is negative 2. Substituting 0 in, 3 times 0 plus 1. 3 times 0 is 0, plus 1 is 1. Substituting 1 in for x, 3 times 1 plus 1, 3 times 1 is 3, 3 plus 1 is 4. So at x is equal to negative 1, y is equal to negative 2. I'm just going to put a little guiding point there. At x is equal to 0, y is equal to 1. And at x is equal to 1, y is equal to 4. Now look to see whether you're inclusive or exclusive at that endpoint. We're inclusive, so we're going to have a solid dot at 1, 4. So I'm going to make this dot a little bit larger for emphasis. And then I can just connect these dots overall for a rough sketch. And it goes on forever. So we put an arrow, an endpoint, an arrowhead on it. Now the second function is governed between positive 1 exclusive and positive 2 inclusive, and that's the function 2x squared. So really I'm just going to test positive 1 and positive 2 because those are the only two integers that are relevant here. So when x is equal to 1, we get 2 times 1 squared. 1 squared is 1. 1 times 2 is 2. When x is equal to 2, we get 2 times 2 squared. 2 squared is 4. 2 times 4 is 8. So at x is equal to 1, and we are exclusive at that endpoint, so we're going to have a hollow dot at 1, 2. But we're going to have a solid dot because we're inclusive at the other endpoint at 2, 8. And this is an exponential function, so it's going to be a little bit curved like this. And then finally, this third function, 3x minus 2. We're testing values greater than or greater than 2. So I want to see what occurs at the endpoint of 2, and maybe I'll test 3 and 4 just to get a sense of what's going on. So when x is equal to 2, we're going to have 3 times 2 minus 2. 3 times 2 is 6. 6 minus 2 is 4. At x is equal to 3, we're going to have 3 times 3 minus 2. 3 times 3 is 9. 9 minus 2 is 7. At x is equal to 4, we're going to have 3 times 4 minus 2. 3 times 4 is 12. 12 minus 2 is 10. Now at the endpoint, we are exclusive, so we're going to have a hollow dot at 2, 4. So we're going to have a hollow dot at 2, 4. Then I'm just going to place guiding points at 3, 7. And at 4, 10. That's all the way up here. So it kind of goes off my graph a little bit. But you really only need 2 points to connect and make a line, of course. So the green function would look something like that. Okay, if there are any questions, then please let me know. I have a few more examples here, but I want to jump ahead to make sure that we are able to discuss the absolute value. So if we have time, we're going to come back to those examples. So I'd like you to evaluate the following absolute value functions at their given inputs. So f of x is equal to 3 times the absolute value of x minus 3 quantity plus 1 when x is equal to negative 2, when x is equal to positive 1, and when x is equal to positive 3. So you're going to substitute these values in. So you're going to end up doing 3 different problems here. You have 3 different answers. You're going to substitute the inputs negative 2, positive 1, and positive 3 in for x. Make sure that you do everything inside the absolute value first, and then you evaluate, and then you do the values on the outside. When evaluating, remember that the absolute value represents the distance that number is on a number line from 0, but practically speaking, it just makes everything positive. Now, when we get to solving equations with variables, there's going to be an extra little subtlety that's added in there. But for now, just remember that it's just the real distance from 0 on a number line. So substitute these values in and evaluate. I'm going to give you 3 minutes, and then we'll go through the solution. Okay, so if we're asked to evaluate at x is equal to -2, +1, and +3, first of all, know that this is another way of asking that question with function notation would be to ask you to evaluate to ask you to evaluate f of -2, f of +1, or f of +3. So if they've already defined the function, this particular function, to be f of x, then when they insert a value for x, that's asking you to evaluate for that particular input by substituting in that value for the variable x wherever you see it. So if there's more than one x, then you're substituting in more than one time. So here, f of -2 would be equal to 3 times the absolute value of -2 minus 3, quantity plus 1. -2 minus 3, we can use the rule leave, change, change to make that a little bit simpler. Leave the first value alone, change the operation from subtraction to addition, change the sign of the number from positive to negative. -2 plus a -3 is a little bit easier to think about or wrap your mind around rather than -2 minus a +3. So sometimes it helps. So that will simplify into 3 times the absolute value of -2 plus a -3 is going to be a -5, quantity plus 1. The absolute value of -5 is just +5, so this will turn into 3 times 5 plus 1. 3 times 5 is 15. 15 plus 1 is 16. So the answer to 1A is 16. For B, if we're evaluating f of +1, then we'd have 3 times the absolute value of 1 minus 3, quantity plus 1. 1 minus 3 is going to be -2, so we're going to have 3 times the absolute value of -2, quantity plus 1. The absolute value of -2 is just +2, so that's the same thing as 3 times 2 plus 1. 3 times 2 is 6. 6 plus 1 is 7. If you have any questions, then please let me know. F of -3 would be 3 times the absolute value of, f of +3. I don't know if I think I said -3. F of +3 would be 3 times the absolute value of 3 minus 3, quantity plus 1. So inside the absolute value bars, 3 minus 3 is 0. So we're going to have 3 times the absolute value of 0 plus 1. The absolute value of 0 is just 0, so that's the same thing as 3 times 0 plus 1. 3 times 0 is 0. 0 plus 1 is just 1. So the answer to 1C would be 1. If you have any questions, then please let me know. Otherwise, I'll give you 3 minutes. I'd like you to look at question number 2. It says g of x is equal to 3 times the absolute value of x plus 1, quantity minus 10, and you're going to evaluate g of -3, g of +2, and g of +5. So if g of x is equal to 3 times the absolute value of x plus 1, quantity minus 10, then g of negative 3 would be equal to 3 times the absolute value of negative 3 plus 1, quantity minus 10. Negative 3 plus 1 is going to be negative 2, and then the absolute value of negative 2 is positive 2. So this is going to end up simplifying into just 3 times positive 2 minus 10. 3 times 2 is 6. 6 minus 10 is negative 4. G of positive 2 is going to be 3 times the absolute value of 2 plus 1, quantity minus 10. That's equal to 3 times the absolute value of positive 3. That's the same thing as 3 times 3 minus 10, which is 9 minus 10, which is the same thing as negative, or simplifies into, I should say, negative 1. And finally, we have g of positive 5. So we're going to have 3 times the absolute value of 5 plus 1, quantity minus 10. So 5 plus 1 is 6. The absolute value of positive 6 is still positive 6. So we're going to end up with 3 times positive 6 minus 10. 3 times 6 is 18. 18 minus 10 is positive 8. If you have any questions, then please let me know. Otherwise, I'll give you 3 minutes. Please look at number 3. Okay, looking at the first value, h of negative 3. So substituting negative 3 in for x, we're going to get 6 times the absolute value of 2 times negative 3 minus 10 quantity plus 2. 2 times negative 3 is negative 6. Negative 6 minus 10 is the same thing as negative 6 plus a negative 10. So we're going to have 6 times the absolute value of negative 16 plus 2. The absolute value of negative 16 is just positive 16. Positive 16 times 6 is 96. 96 plus 2 will be 98. The second value, h of 1, substituting 1 in for x, we're going to have 6 times the absolute value of 2 times 1 minus 10, quantity plus 2. 2 times 1 is 2. 2 minus 10 is negative 8. So we end up with 2 times the absolute value of negative 8, quantity plus 2. The absolute value of negative 8 is positive 8. 2 times positive 8 is 16. 16 plus 2 gives you 18. And h of 2, we have 6 times the absolute value of 2 times 2 minus 10, quantity plus 2. 2 times 2 is 4. 4 minus 10 is negative 6. The absolute value of negative 6 is just positive 6. So 2 times positive 6 is 12, plus 2 will give you 14. If you have any questions, then please let me know. Otherwise, in our last few moments, I just want to mention these concepts, the following concepts, and these will come up later in subsequent videos that we do. I'm going to go through them just for you, and we'll just have a little bit of a discussion, and this will bring us up to the end of class. So general transformations of the absolute value function. This is actually a parent guiding function for all functions that you can use with graph transformations. And so it's in the function, if you have some parent function here, we have the absolute value. So we have these absolute value bars. So this is a representative of an absolute value function. Now what you need to know is that this a value up here, this is all equal to y, by the way. We could either say f of x, y, or we could say f of x. But we could say y or f of x is equal to a times the absolute value of x minus h, quantity plus k. And we'll get much more into this in more detail later. But this a value is a stretch or a shrink factor. And actually, let me go ahead and show you what this function looks like. The absolute value function is a pretty common piecewise function, and it just looks like a V. So it's exactly symmetrical with respect to the y-axis, and it looks like a straight V, whereas y squared is, the parabolas are kind of U-shaped. They have a curve at the bottom. This meets at a point at exactly at the origin. So what we're talking about here, we have a parent function of y is equal to the absolute value of x. A is a stretch or shrink factor. H is a horizontal shift. And by horizontal shift, I really mean a shift in the vertex. So right at the corner of that function. And K is a vertical shift. Now the thing to really watch out for, and which gets a little bit confusing, is that in this format, in this function format, notice that h has a negative sign next to it, but k has a positive sign next to it. The implication of that is that the horizontal shift, the h value, looks like it seems opposite common sense. And obviously that is not a mathematical term, but that's helps me remember what's going on. So if it's opposite common sense, if it's negative 2 next to the x, normally with respect to x, you would think that means left 2. But if it's opposite common sense, if it's the absolute value of x minus 2 inside the absolute value bars, then that's indicative of a shift right 2, because the h value is opposite common sense. If the k value, though, this goes with common sense, because it has an addition sign next to it. So it doesn't have any function, any value that's negating the number itself. So let's just look at one example, and again, I'm going to do a whole series on this later, but this is just a taste. So number one, if f of x is equal to the absolute value of x, what is the equation of f of x shifted 2 units left and 3 units down? So if we're going left 2 and down 3, so left, a shift left or right, that's your h value. A shift up or down, that's your k value. Your h value, again, is opposite common sense. So if you're going left 2, that normally on the x-axis would mean -2 or -2, but it's opposite common sense, so this is going to be +2. K goes with common sense, so if we're going down 3, it's going to be -3. So our function here would be f of x is equal to the absolute value of x plus 2, quantity minus 3. We have our h value right here, and we have our k value right here. So that was just a very brief introduction. I promise that we will get into that in much greater detail. However, if there are any questions, then please let me know. You can send them over in the live chat feed, or you can drop a comment in the comment section below. If you find these videos helpful, please like my stream and subscribe to my channel. I appreciate it very much. I'm live every day, every week for you guys. I'm also available on my social media if you have any particular questions or recommendations, or if you get stuck on a homework assignment or project, you can reach out to me, and I'm always available, or do my best to be available. But otherwise, thank you guys very much for watching. And Dr. Todd, do you want to say goodbye to everybody? Hey, Dr. Todd, come on, you want to say goodbye? Come on, you got to say goodbye to everybody. That's your job. Come on. You say goodbye. Say goodbye. Come on, you do a paw. Just say goodbye. All right, very good. All right, thank you guys very much for watching. I'll talk to you all soon.